Hello guys, in this video I'll talk about lenses, that is the reflection of light or the refraction of light through lenses, and I'll solve several examples that will help you to understand better. So I will advise you don't skip around this video. A lens is an optical system with two refracting surfaces, and then it can be converging, it can be diverging. So we can have something of this nature. This is called a biconvex lens. This is called a biconvex lens. You can have something of this nature too. This is called a biconcave lens. Okay, it has two refracting or reflecting surfaces. So, and that's why it is called a lens. Okay, now we can also be something of this nature. You can also have something of this nature. This side is plane and this side is concave, as in a biconcave lens. Okay, so this is called a plano concave. Plano concave. So if I have something of this nature, that will be plano convex, that is plane, and it has one of the side of a convex lens. So this is referred to as plano convex lens. Okay, and then we have something of this nature, which is referred to as a meniscus. Okay, so these are the different lenses that we have. Okay, and the common ones, there may be others, but the common ones. So when we talk about a converging lens, we're talking about a convex lens. Okay, a convex lens, that is, it is the one that converges all rays of light at the focal point. Okay, and the kind of images, the characteristics or the nature of the image that is produced, it is dependent on the position of the object, just like that of a converging mirror. So I will consider some few positions now, so that we will see the characteristics of the images that are formed. Since it consists of two reflecting surfaces, most times we deal with the reflecting surfaces differently. So let's say I want to talk about this particular surface now, the rear mirror, the mirror at the back, like this one now. It should if I extend its sphere, since a lens is like part of a sphere, like the one of the arcs of a sphere or of a circle, and we used to say that the center of that particular sphere is the center of curvature, and then the middle of the center of curvature and the middle of that particular sphere is the focal point. So I'll say this is f1, and I can say this is f2. You can see this is f1 and this is c1. That means the one for the other one from the front, that is this one too, it will have its own too. So I'll have something of this nature. I'm not drawing it to scale, so just bear with me. So the center of that particular, we call it the center of curvature, and the middle from the pole to the center of curvature, the middle is called the focal point. Okay, so that's majorly what we normally have. So I can call this my f2 and I can call this my f1, but because this is rare, we always refer to this as f2 in most textbooks, and this as c2, and then this as f1, because this f1 is due to the reflecting surface in the front. Do you understand now? So we refer to this as c1. Okay, the distance from this point to this particular center is just like when you have a circle like this. This is the center from here to here, and you call the center of curvature. That means from this point to this point will be referred to as the radius of that particular curvature, isn't it? And I said that the middle is the focal point. Okay, then, and the distance from the focal point to that particular center is small letter f, which is referred to as the focal length. It will mean that the focal length is equal to the radius of curvature divided by 2. Now let's consider those positions. So this is a converging lens, it converges the rays of light. I just want to draw a line to show the middle, the center of that particular lens. So we can pick a point as the center of curvature and this point as the focal point. It will have another focal point. It will have another center of curvature. An object is whatever you place in front of the optical system or the mirror or the lens. So the rays of light will move. Let me just draw a line to show the middle of the lens, the center of the lens. So this is the center of the lens. Now that means it will converge it, isn't it? And it used to converge at the point that is referred to as the focal point. And of course, if another rays of light will also pass through, because they need to touch each other so that image will be formed. So the second one will usually pass through the center of the lens, that is the pole. The center of the lens is referred to as the pole or the vertex. So it's the image will be formed where they are touching each other, where the rays of light are touching. And whenever the images are formed below the optical line, or the principal axis, or the optical axis, this straight line is called the principal axis. This straight line is called the principal axis. Okay, so whenever images are formed below the principal axis, it is always inverted, that is, it is always upside down. Okay, so it is upside down and it becomes smaller. So the characteristics of this is that it is real. The image is real. It is real because the image is formed in the direction of the outward ray. This side of the lens is called the inward ray. Okay, because you can see that the light is going into the lens here at this part. So this is the outward ray, that is, the light is coming out of the lens from here, isn't it? So it is very correct. So when images are formed on this side, it is real. When images are formed along the direction of the outward ray, the images are real. And two, it becomes inverted. It is inverted because it is formed below the principal axis. And then the third one is that it is diminished. It becomes smaller. It becomes smaller in size. Okay, so let's say I want to consider another position now. It passes through the center. So it will be formed somewhere here. So the image is formed at exactly the center of curvature. If you draw it to scale, it will be formed exactly, but this is not up to scale. But if it is drawn to scale, it will fall exactly under the center of curvature. And of course, this is under the center of curvature. So one, it is real because it is formed along the direction of the outward ray. So we use this outward ray and inward ray because we are talking about lens which has two sides, two reflecting surfaces. So the other one is that it is inverted. Another one is that it is of the same distance. Okay, because this is C, that is from this point to this point is center of curvature. Are you with me? So this is the object distance U, and of course this is the image distance V. So the image distance, it is possible they don't have the same distance, because sometimes the center of curvature of the first of the, for instance now, of the rear surface, the center of curvature may be different from the center of curvature depending on the nature of that particular surface. This surface with this arrow may have a center of curvature, may have a radius of curvature that is probably 20 centimeter, and this one may have a radius of curvature that is not 20 centimeter, it may be 30 centimeter. That means the object distance here, which is on the center of curvature, which is the same thing as r, will be 30 right here, but it will not be 30 for here. It will be it will also be 20, it will be 20 centimeter. So depending on the radius of curvature of the different surfaces. Okay, so you may not have the same distance, but it will have the same size. It will have the same size. Okay, they will possess the same size, that is the height from this point to this point. Let's say it is y, then from this point to this point, we also, let's say it is, okay, let's just say y is the image height, and this is the object height. So same size means the image height will be equal to the object height. So if I place an object at this particular center of curvature, light will travel, okay, and then it will pass through the center of curvature. Okay, so another one will pass through that particular center, and then it will move this way. Okay, so the image is formed beyond C, and of course if you look at it, it is magnified. So one, it will be real. Two, it is inverted, and you know the reasons. And three, it is formed beyond C. It is formed beyond C, and it is magnified. So the first position that we put it, that is beyond C, we got an image at this point. The second one, we got an image at this point. So this actually gave us an image at this point now. So it's like sequential. So when it is here, it is diminished. When it is here, same size, and now it is magnified. So now let's see the next position. What will happen? That means the object will now be at the focal point, now exactly at the focal point. So if I place an object at exactly the focal point, it will move this way. If I draw it to scale, it should pass through the focal point. Okay, now the other one should pass through the center as well, so it begins to go. So it just goes straight down. It should pass through the center. Okay, so it goes straight down. If you draw it up to scale, that means it will not touch each other. So one of the characteristics is that no image is formed, but because we believe that an image should be formed, so sometimes we say that the image is formed at infinity. That is, the image is formed at a very far place. Okay, now let's talk about a point that is lesser than the focal point. Okay, so if I place an object at this point very close, the first position we consider was between F and C. The next one was exactly at C. The next one is formed beyond C. The next one is formed at infinity. Now we want to consider the last one. We want to see where it will be formed. So as the rays of light is directed towards the focal point, we should have a virtual ray. We should have it in this direction. Okay, we should have it in this direction. So the same way, there should be a light passing through the center of curvature too, and it will be, so we should also have another ray of light, a virtual ray of light. So they should touch each other at a point somewhere here. Okay, so that means how it is magnified. So one, it is not real because it is supposed to be formed in the direction of the outward ray. We have it now in the direction of the inward ray, and of course it is formed by virtual rays of light. So that's another proof that it is virtual. So we have a virtual image. So whenever you are considering, and whenever we have a virtual image, the image distance should be negative. So v will be negative here. V is the image distance. Okay, so the negative sign is what tells us that the nature of the image is virtual. So two, it is erect or upright, that is, it is not inverted, that is, it is formed at the top of the optical axis. I told you this line is called optical axis. So it is erect. or upright. Okay, so and the third characteristics is that it is magnified. So if you have a question that says a converging lens is used to form an erect image, so you know that they are talking about this particular scenario, and of course the image distance will be negative. Now if they say it is magnified or it is used as a magnifying glass, the image will be negative because it is going to form a virtual image. Okay, so how about we have a diverging lens? A diverging lens looks like this. That is, the center is thinner than the edges. Okay, so that's the descriptor. But for a converging lens, the center is thicker than its edges. Okay, so it will have a focal point and the center of curvature the same way, a focal point and the center of curvature. So we can see this f1, c1, f2, just like the others that I explained. So if I place an object in any of the position, the characteristics of the image that is produced is VED. That is, it will be virtual, and I'll explain why it is virtual. It will be erect. If an image is erect, it means it is upright. It means it is formed at the top of the optical axis, and it will be diminished. That means it will be smaller than the object. Okay, so if I place an object at this point, okay, so the rays of light, let's say this is the middle of that particular lens, the rays of light will approach it, isn't it? And then it will diverge it, isn't it? So if it diverges it, we should have virtual rays of light going in this direction, and it should pass through the focal point. So it will look like this ray of light, this particular ray of light, with this blue, with this particular ray of light, it will look like it is diverging from this point. Meanwhile, it is not. It is actually coming from the object, and that's why we say that diverging lenses have virtual focal point, because they have because light rays don't truly diverge from its focal point. It only appears to diverge from its focal point, so we say it is virtual. So the light appear to diverge. It is not really it is not even diverging from that point. We just formed a rays of light along that path. So that's the way it is. If another rays of light goes like this, it will diverge it, isn't it? So there will be a virtual rays of light going through the focal point. So that's why we say it appears to diverge. It's not like the light rays are really diverging from that point. Okay, and that's why the focal point of a diverging lens is negative. So diverging lens have negative focal points, and it also has a negative radius of curvature. Okay, that is, from this point to this point is this the radius of curvature. So it has a negative radius of curvature, it has a negative focal length, it has a negative image distance, and that's why the image is virtual. So if I produce another rays of light now to pass through the center of the lens, okay, so where it touches each other, that's where the image will be formed. That means the image should be formed somewhere here. So the image is erect truly because it is formed on the top of the optical axis, and then it is virtual because it is formed by virtual rays of light. Okay, and it is formed around the inward rays of light. So it is virtual. That means the image distance will also be negative. So these are the things to take note of anytime you have a diverging lens: negative focal length, negative radius of curvature. If the focal length is negative, the radius of curvature will also be negative. So that's the way it is in calculation. Now let's consider some other things that are very important. For instance, the magnification, that is the linear magnification, is image height divided by the object height equal to the image distance divided by the object distance. V is the image distance. We always have everything about the image at the numerator, while hi is the image height. So h naught is the object height, u is the object distance. Okay, and this is the formula we will use throughout the video. 1 over v plus 1 over u equal to 2 over r. The reason we have 2 over r is because f is equals to r over 2. That means 1 over f is equal to 2 over r. I know that some text may use negative sign right here as the length equation. Okay, but for this video I will stay with this formula, okay, that we normally use for mirror, and it will be correct. So far we obey the sign convention. Okay, there are several ways to solve questions on lens, but I'll stick to a very simple method of solving it and getting the right answers. Okay, a convex lens of focal length 10 centimeter. A convex lens, that's a converging lens. So f is positive, that's 10 centimeter, is used to form a real image which is half the size of the object. That means the image height is equal to an half of the object height. How far from the object is the image? How far from the object is the image? You need to be aware that's not the image distance, for because the image distance is the distance of the image from the mirror or from the lens, not from the object. So when we talk about from the object, what that simply means is, let's say this is the object, and let's say a real image, because the question says real image. Real images for a converging lens is formed at the other side of the lens, so it is not formed in the same position. So we need to know that from this point to this point is the object distance u, and from this point to this point is the image distance v. All right, that means how far from the object the image will be u plus v. Okay, so I need to find u and I need to find v. But if it were to be, if the question had said erect image or upright image or virtual image, in converging lens, the only time we had a virtual image formed, that was the last, I think that was the last position that we considered, and the image was formed behind the object and it became magnified. Or if the question had said magnified image, so that means from this point, that was the last position that we consider. You can check it when the object is placed, when the object distance is less than the focal length, and we had something like this, we had something like this, we had something like this. Okay, so you will see that the image distance is v and is u. So the distance of the image from the object, that will be v minus u. Okay, so that's that. You just need to understand that. So now to find u plus v, I need to first of all find my u and I need to know my v. So to do that, I need to make use of that formula, that beautiful formula, which is 1 over f equal to 1 over u plus 1 over v. And of course, I don't know my u and v, two unknown. I need to do something about that. From this point where image height is equal to object height, it is possible for me to say that magnification is image height upon the object height, which is equal to v upon u. That means I just need to use this. Okay, so but from the question, the image height is half of the object, so this is the image height, and of course upon the object height is equal to v upon u, which means that this can cancel out to give us v over u equal to half, isn't it? And that simply means that v is equal to 1 over 2 of u. That is, if I cross multiply, okay, if I cross multiply, now if v is 1 over 2 of u, it is the same thing as 0.5 u. So 1 over f is 10, equal to u is still u, but v is now 0.5 u. Okay, so I can find my LCM, which is 0.5 u, and this will give me 0.5 plus 1. That's equal to 1.5 upon 0.5 u, which is 1 over 10, which means 1 over 10 is equal to 1.5 upon 0.5 u. That means 0.5 u is equal to 1.5 times 10, which is actually equal to 15. That means u is equal to 15 divided by 0.5, which is equal to 30 centimeter. If u is 30 centimeter, we have seen it that v is half of u. So the half of 30 is what? Is 15 centimeter. So the image distance is 15 centimeter. As a result, our v plus u will be equal to 30 plus 15, that's equal to 45 centimeter, and that's option A, very correct. So let's go to the next problem. A diverging lens of focal length 20 centimeter forms an image half the size of the object. What is the object distance? A diverging lens, that's a concave lens, so it has a negative focal length and is given as 20 centimeter, forms an image half the size of the object. It forms an image height is equal to, or image size is half the size of the object. Okay, so sometimes, many times, in fact all times, I use image height as image size. It is comparable. So is half the size of the object. So what is the object distance? Object distance is u. So what is u? Okay, but we know that for this kind of problem, v is also negative, r is also negative, isn't it? Those are the characteristics. So it will be very simple if I just say that since hi is equal to half of h naught, it means that hi over h naught, just like I did in the first example, will be equal to half, and it will be equal to v over u, which means that v is equals to u over 2, or 1 over 2u, which is the same. So I can have 1 over f, that will be minus 20, which is equal to 1 over v, and of course v is negative, that's minus 1 over 2u, isn't it? Minus 1 over 2u. And I'll prefer to write it as 0.5u, just to avoid this fraction. 0.5u plus 1 over u. Okay, so I can find the LCM, which is supposed to be minus 0.5u, and this will be 1 plus this. I will have minus 0.5. Okay, that means 1 minus 0.5 is 0.5 upon 0.5u, negative sign, don't forget. Okay, that's minus 1 over 20. So this negative sign should cancel out this negative sign. So I will have 1 over 20 equal to 0.5 should cancel out 0.5. So I should have it to be equal to 1 upon u. That means automatically u is equal to 20. U is equal to 20 centimeter. And that's very, very correct. But I noticed that this same problem has been causing many confusion online. So I just want to show you a proof why it is correct. Many said the answer is supposed to be 60 centimeter. Some people said it is 45 and things like that. But let me just quickly show you another method that you will never be wrong if you solve it that way. So when we talk about a diverging lens, we are talking about something of this nature, isn't it? We are talking about something of this nature. And of course, this is the principal axis. Okay, so let's say I place an object right here now. Okay, and this is the object height, that is the height of the object. So it will have to move this way and then diverge. Okay, so and of course there will be a focal point that which the light will appear to diverge, and of course I'll have another light which is supposed to pass through the midpoint of that particular lens. So I will have something of this nature. So the image will be formed right here. Okay, and it will be erect. So this is the image height. All right, so I have two triangles. I have this particular triangle. Okay, I have this particular triangle, and I have this particular triangle as well. If I draw it out now, this is what you will see. Okay, so I have a big triangle and I have another small triangle inside of it, isn't it? This is half h naught according to the question, and then this is h naught. This is the object height, this is the image height. But don't forget, image height is half of the object height. Okay, and from this point to this point, if you look at it very well, that's the object distance u. Okay, that's the object distance u, and of course this is capital letter F, the focal point, which means that from this point to this point is small letter f, isn't it? And from this point to this point is the image distance v. So that means this is v and this is u, the big one is u. Okay, so if because the triangles are similar because they have the same angle right here, let's say angle theta, so that makes the triangle similar. And if they are similar, the ratios of their corresponding sides will be equal. That's very correct. That means I can have half h naught upon h naught. Because the triangles are similar, the ratio of their corresponding sides will be equal. So this upon this is the same thing as this upon u. Okay, so I can cancel out this, and then I will see that half is equal to v over u, which was the formula for that particular magnification. So from there I can actually say that if I cross multiply, I can say u is equal to 2 of v. So I need to know my v to know the final answer. Now let's see another triangle. There are two triangles in view. This is the second triangle, this particular triangle with the virtual rays of light. Okay, so I have that particular triangle, and this side of the triangle, this side of the triangle is the same thing as h naught. So I can have h naught right here. So that's h naught, which is the image height. This side is half of h naught, that is the object's height. And from this side to this side is v, which is the image distance. And from this side to this side is f, that's the focal length. Okay, that means this place will be f minus v. So because the ratio of the triangles are equal, I can say that h naught, half h naught upon h naught is equal to, if I use this one, then its side should also go first. That's f minus v upon the side of the bigger triangle too, which is f. Okay, I hope you understand that. If I make use of this, if I said that, if I said this upon this, then I should have this upon the long one. So the same way, so this we just have to cancel out with this. And the f, we know the f from that particular question. The f is 20 centimeter. In this case it is not minus 20 centimeter because we are dealing with the ray diagram now. It's just like they are telling us the focal length is 20. That means the distance from this point to this point is 20. Take a ruler and measure 20 centimeters. So that's the way it is. It's not negative when we are dealing with ray diagram because this is the practical aspect. So that's over 20. So I can have something of this nature. That means 1 over 2 is equal to 20 minus v over 20. Okay, so if I cross multiply that, I should have 20 over, no, I should have 20 equal to 2 into 20 minus v. That means if I do something of this nature, so I should have 20 equal to 40 minus 2v, which means that 2v is equal to 40 minus 20. That is, if I take negative 2v to the other side of the equation, and 40 minus 20 is 20, that means 2v is 20. That means v is 20 divided by 2. That means v is actually 10. So if v is 10, u is equal to 2 times 10, which is 20 centimeter, which is very correct. Okay, so let's solve the next problem. An object of height 3 centimeter is placed 10 centimeter in front of a biconvex lens. A biconvex lens is a converging lens. So an object of height, so the object height is 3 centimeter and is placed 10 centimeter. That means the object is 10 centimeter from the convex lens. That convex lens has a focal length of 15 centimeter. The image of the object is what? The image of the object. So we are looking for the characteristics of the image. So we need to find v. To know v, I just need to go with my formula, which is 1 over f, where f is 15 and is equal to 1 over u, where u is 10. That's supposed to be 1 over 10 plus 1 upon v. So I have 1 over 15 minus 1 over 10, which is equal to 1 over v. 1 over 15 minus 1 over 10 is supposed to be 1 over 30, which is equal to 1 over v, which means that negative, which means that v equals to minus 30. And if v is equal to minus 30, I should have something of this nature. Oh, it will mean that v is virtual. So the ones with virtual, okay, virtual. Now to know the tallness, that is the height of the image, I need to consider the magnification formula, which is h naught hi upon h naught equal to v upon u. And of course the hi is what we are looking for, the image height. And of course the object height is 3 and v is 30 centimeter, then u is 10 centimeters. So I'll have something of this nature. That means image height is 3 times 3, 9 centimeter. Alright, so I have it 9 centimeter tall. So option C is the right answer there. So it is true that the image is negative, it is virtual. If you look at it very well concerning the explanation I gave in the first minutes of the video, you will see that u, which is the object distance, is less than the focal length. And of course u is 10 centimeter and the focal length is 15. So the kind of image that will be produced will be magnified, and it should be formed at the same position where the object is, not on the other side of the lens. So let's consider another example. An object placed 20 centimeter from a converging lens forms a magnified clear image on the screen. When the lens is moved 20 centimeter towards the screen, a smaller clear image is formed on the screen. Calculate the focal length of the lens. Sometimes when we have the lens to be moving probably towards the object or the image, we may need to draw so that we'll have a perfect answer. So it is initially 20 centimeter, the object distance. Okay, and this is supposed to be the image distance. The screen is where the image is formed. And if we choose that our image is formed at the other side of the lens, then it should be positive. Okay, and of course it will mean that V is the image distance and 20 centimeter is the object distance. So, and for the other point of the question too, when I place an object right here and then this is a lens, the object distance is now 40 centimeter because the lens has now been moved from away from the 20 centimeter mark to another 20 centimeter towards the screen. So it was actually in the 20 centimeter mark, but now it has been moved by another 20 centimeter towards the screen. So the object distance will increase to 40 centimeter, and this remains the image distance V that we don't know and we are actually looking for it. It means that if this place to this place is x, and of course these two will be x, but the difference is that this will be x minus 20. That's why we need to make use of this assumption that if the length from the object to the image is x, the then the image distance v should be x minus 20, and this will be x minus 40. At least this will differentiate between the image distances of the two scenarios. If we had left it at v and v, it wouldn't have been correct because the image distance changed. So, and leaving it as v would mean that nothing had happened, it has not changed. Okay, so we just need to, as the object distance changes, we need to find a way to make sure that the image is also changing correspondingly. So we needed to know the exact value, the exact distance from the image to the object itself, which is assumed to be x. So it will mean that 1 over f for the first scenario is equal to 1 over u, which is 20, plus 1 over v, which is x minus 20. And of course, in the second scenario, I will have 1 over f to be 1 over 40 plus 1 over x minus 40. So I can actually say that 1 over f is equal to 1 over f because I'm dealing with the same kind of lens. That means 1 over 20 plus 1 over x minus 20 is supposed to be equal to 1 over 40 plus 1 over x minus 40. So by I can actually call it like terms and say that 1 over 20 minus 1 over 40, or we can do it several ways, which is supposed to be equal to 1 over x minus 40 minus 1 over x minus 20. So I can have this in brackets. 1 over 20 minus 1 over 40 is supposed to be equal to 1 over 40, which is equal to 1 upon x minus 40 minus 1 over x plus 20. So by LCM on this other side, I can have something of this nature. So I'll have my LCM, which is supposed to be the product of x minus 40 and x minus 20. So by LCM, I should have x minus 40 in this to give me x minus 20, and then minus, I should open a bracket since I'm now dealing with negative sign, then this x plus 20 x plus 20 is never a plus. Minus, so there's a mistake right here. Is never a plus. So x minus 20. So I should have something of this nature. X minus 20 in the denominator, that should give us x plus 40, okay, which is equal to 1 upon 40. So that should be x negative 20 minus x minus 40 at the numerator by opening the bracket with this negative sign. So that I should have x minus 40, okay, x minus 20, which is equal to 1 over 40. All right, so x minus x gone, and the minus 20 minus 40, that's supposed to be, this is minus. Why am I writing positive? Okay, so negative, it is always negative. So minus times x is minus x, minus times minus 40, that's supposed to be plus 40. X minus x gone, minus 20 plus 40, that's supposed to be 20 plus 20 upon x minus 40, then x minus 20, which is equal to 1 over 40. All right, so I should have something by cross multiplying. If I cross multiply, I should have something of this nature. I should have something of this nature. X minus 40 into x minus 20 to be equal to 800. Okay, and of course, if we expand this bracket, that should be x squared minus 20x minus 40x plus 800. That is, x times x is x squared, x times minus 20 is minus 20x, minus 40 times x is minus 40x, minus 40 times minus 20, that should be plus 800, which is equal to 800, which means that x squared minus 60x plus 800 minus 800 is equal to 0. So this is x squared minus 60x equal to 0. That means x squared equal to 60x. So this can actually cancel out this, and it will mean that x is equal to 60 centimeter. But that's not the answer. X is not what they ask us to find. The question says calculate the focal length. So to find the focal length, I need to use 1 over half. Okay, 1 over half equal to 1 over v plus 1 over u. So if I use this particular scenario, my u will be 40 and my v will be x minus 40. So that will be 1 over half, which is equal to 1 over u, that's 40, plus 1 over v. V is x minus 40 and x is 60 minus 40. Or if I use the first scenario, which the object distance is 20 plus the image, which is x minus 20, and now x is 60, then minus 20. So 1 over half will be equal to 1 over 40 plus 1 over 20, or 1 over 20 plus 1 over 40. You can see it is the same. So 1 over 40 plus 1 over 20, that's supposed to be equal to 3 over 40, 1 over half. So by cross multiplying, it will mean that, if I cross multiply, it will mean that, or if I reciprocate both sides, it will mean that f is equal to 40 over 3, which is equal to 13.33 centimeter. Okay, so that's just it, and that's option E, which is very, very correct. Used as a magnifying glass, The image of an object 4 centimeters from a converging lens is 5 times the image of an object 4 centimeters. That means the object distance u is 4 centimeters. 4 centimeters from a converging lens whose image size is equal to 5 times the object length. Okay, so what is the focal length? What is the focal length? Now, but one of the important things to note is that a magnifying glass, for a converging lens to magnify an object, or for a converging lens to be used as a magnifying glass, the image has to be virtual. If you remember the last scenario where we talked about putting the object at a point that is lesser than the focal length. Okay, so let's say I put the lens right here. The kind of image that is formed will be virtual, and to be somewhere here to be magnified. Okay, if you remember the last scenario of the converging lens. Okay, in the first minutes of the video you can check it. So I will now have something of this nature. It will mean, and one of the consequence of this is that v is negative, because it will form a virtual image that is in the same position as that of the object. Okay, so that means my image distance has to be negative. Okay, but before we get to that point, let's consider this formula and see, because to find the focal length I need to use this formula, 1 over v plus 1 over u. So I know the u, I need v now. To find the v, I can make use of v over u equals to image height over object height. But now the information given from the question dictates that image height is 5 h naught. So I can cancel out this, which will mean that v over u is equals to 5. That means v is equal to 5u. So because v should be negative, I can say that v is minus 5u, because it has to be virtual for a converging lens to produce to be used as a magnifying glass. I hope you understand. So 1 over f is equal to 1 over minus 5u plus u. Okay, u, and of course I know my value of u. Let me just go straight. Minus u is 4, so 5 times 4, that's 20, and then u is 4. So it will mean that 1 over minus 20 plus 4, 1 over minus 20 plus 4 is supposed to be equal to 1 over 5. 1 over 5. That means 1 over f is equal to 1 over 5, which means that f is 5 centimeter, which is very, very correct. So that's how it is. So anytime, even if converging lens is not included in the question, whenever a magnifying glass is being mentioned, because a magnifying glass actually uses a convex lens, it does not use a diverging lens. A diverging lens has three characteristics: virtual, erect, and diminished. It does not magnify, so we only use converging lens. And there are two scenarios where converging lens produce a magnified image. It produces a magnified image when you place the object between the center of curvature and the focal point, that is between the center of curvature and the focal point. We are going to use to have something of this nature. If you can remember, you can check the first minutes of the video. We had something like this, and the object was formed beyond c. Okay, so it was magnified. And then we have another scenario where we place the object less than the focal point, and we had something like this. Okay, we had something like this, magnified. Okay, so that's it. But for this, v will be positive, and for this one, v is negative, because v is formed in the same position where the object is located. but this one the image is formed on the outward, isn't it? The outward ray or the other side of the lens. Okay, so but if for this question, if you consider this scenario for this question, the answer will not be in the option. The two answers cannot be in the option. So we just have this in the option where v is negative. If you use v as positive, your answer will not be found in the option. That means they didn't consider this particular scenario. So this scenario is very very important and it's very very common. Okay, the image obtained with a converging lens is upright. Now when a converging lens produces an upright image or an erect image, the image is always virtual, and of course the image distance is always negative. Okay, you know that I explained it while I was talking about the different positions that we can place an object in a converging lens, and then it will produce some characteristics of images. Okay, and that's supposed to be the last position I talked about for a converging lens. So the now let's see, the image is three times the length of the object. So image height is equal to three times the length of the object, which means that the image height upon the object height is equal to 3, and is the same thing as v over u, which will mean that v is equals to 3u, right? Now the focal length of the lens, converging lens have positive focal length. So that's it. That's all. So instead of v equals to 3u, I'll have v equals to minus 3u, just because of the word upright, because upright images are only formed in a converging lens once, and that is a situation whereby the converging lens produces a magnified image and a virtual image. Okay, so if I have my formula, which is 1 over f, 1 over 20, which is equal to 1 over v, that's 1 over minus 3u plus 1 over u. So by LCM, I can have 3u as my LCM, or minus 3u, which will be 1, and then minus 3, which will be minus 2 upon minus 3u. Okay, and of course I will have 1 over 20. This negative can go with negative, so that I will have 2 upon 3u, which means that 1 over 20 is equal to 2 upon 3u, which means that 3u is equal to 2 times 20, which is 40. That means u is equal to 40 upon 3. 40 divided by 3 is supposed to be 13.33 centimeter. So I think, oh, that's correct. Object distance. Now let's solve the next question. The radii of curvatures of front and rear surfaces. The radii of curvatures of front and rear surfaces of a thin convex lens are 30 centimeter and 12 centimeter respectively. What is its focal length when placed inside water? Take refractive indices of glass and water to be 1.52 and 1.33 respectively. Now when I have a thin lens is a kind of lens. When we say a thin convex lens, is a lens in which the thickness is negligible. We can neglect its thickness, so we can say it is thin. So let's say we have a thin convex lens that looks like this, and then this is supposed to be the principal axis, isn't it? Now this thin convex lens is given, and we were provided with two radii of curvatures. Okay, so let's say, how do we know the radii of curvatures? Now this first curve surface, now I can extend it. Okay, just like I drew the other time while I was introducing you to it, and the center is the curvature, isn't it? So we can say from this point to this point, that means this point is the radius of curvature. We can say for the front surface, this is r1, and for the rear surface, this is the rear surface, this other one, okay, in black. If I extend it, so this is its radii of curvature r2. Okay, so the radii of curvature of the first one is always given as positive, and if this is given as positive, the other one on the other side should be given as negative. All right, that is for a convex lens. Okay, so one of the equation that I will use to solve this is called lens maker equation, which is given as 1 over f, which is equal to refractive index minus 1 into 1 over r1 minus 1 over r2. Okay, but now if I substitute this negative value, I'll have something of this nature. Or if I just decide to use it directly, but r1 r2, r1 is the radius of curvature of the front surface, r2 is the radius of curvature of the rear surface, while mu is the refractive index that shows the relationship between the glass and the medium that is surrounding it. For instance, in this particular question, we have a glass that is inside water. So we are going to compare it by saying that the refractive index of that particular glass upon the refractive index of the medium that surrounds it. Okay, the medium that surrounds it. So the refractive index of glass as given in this question is 1.52 upon 1.33, and of course if you press this on the calculator, that's supposed to be 8 upon 7, which means that I'll have 8 upon 7 minus 1 into 1 minus r1. Of course, that's supposed to be 30 minus r2. That's minus r2 minus r2, which is 12. Okay, so I should have 1 upon f, which is equal to 8 over 7 minus 1. That's supposed to be 1 over 7 into 1 over 30 plus 1 over 12. Then 1 over 7, 1 over 30 plus 1 over 12 is supposed to be 7 over 60. Okay, so I have 1 over f, then this will get to cancel out 7 7, so I have 1 upon 60, which means that f, the focal length, is 60 centimeters. All right, so that's how we do it. The refractive index shows it shows the relativity between the glass and that particular medium, so we get to divide it and do other things. All right, an object placed 12 centimeters in front of a convex lens produce a virtual image of magnification 3. The focal length is what? So object placed, that means u is equal to 12 centimeter in front of a convex lens produces a virtual image of magnification. So magnification m is 3, and that's the same thing as v over u. That means v is the same thing as 3u, which means 3 into 12, and that's supposed to be 36. But since it's a virtual image, so v will be minus 36. Okay, so to find the focal length, 1 over f is supposed to be equal to 1 over 12 plus 1 over 36. Okay, and of course I'll have something of this nature. 1 over 12 plus 1 over 36 is supposed to be 1 over 9. All right, which means that f is equals to 9 centimeter. All right, a lens is required to have a power of minus 2.5 diopters in air. Lens is required to have a power of this. So power of the lens is minus 2.5, and then the convex front surface diopter, so capital letter D, the convex front surface has a radius of curvature of that. So R1 is 30 centimeter, and of course we are asked to find R2. Okay, now remember the power of a lens is equal to 1 over f, where f is in meters. Okay, and we also have, or power of a lens is also 1 upon 100 upon f, where f is in centimeters. So I'll prefer to go with this simply because I have other parameters in centimeters. Okay, and you can also use this. That means if you use this, you will need to convert this to meters by dividing by 100, and everything will be fine. Okay, so but okay, let's just divide this r1, and then we make use of this which is in meters, so that 30 divided by 100, that's supposed to be 0.3. Okay, so 1 over f equal to refractive index minus 1, then 1 over r1 minus 1 over r2. So r2 is what we need to find. We don't apply sign convention to what we have not found yet, to what is not known. Okay, so refractive index now is the refractive index of the glass upon the refractive index of the medium surrounding it, which is actually air, isn't it? So I have air as the medium that is surrounding it. Since the refractive index of the glass is not given, I use 1.5, which is a kind of standard refractive index for glass. So we use it when the refractive index of glass is not given. Okay, and that of air 1. So I have that. So 1 over f, we know it, 1 over f from that particular formula is given as minus 2.5, which is the same thing as the power of that particular lens. So minus 2.5 is equal to refractive index, which is 1.5 minus 1, into 1 over r1. R1 is 0.3 minus 1 over r2. So I have minus 2.5 to be equal to 0.5. Okay, then 1 over 0.3 minus 1 over r squared. So I divide both sides by 0.5. That means minus 2.5 divided by 0.5 is equal to 1 over 0.3 minus 1 over r2. So 2.5 divided by 0.5, that's supposed to be negative 5. So minus 5 will be equal to 1 over 0.3 minus 1 over r squared. Okay, so I can have minus 1 over 2 transferred to the other side of the equation so that it becomes positive, and then it will be equal to 1 over 0.3 plus 5. So 1 over 0.3 plus 5 is the same thing as 25 over 3. That's supposed to be equal to 25 upon 3, which means that r2 is 3 upon 25, and 3 upon 25 is the same thing as 0.12 in meters. Don't forget we are solving in meters, and that's the correct answer. So this formula is a very important formula. It's referred to as the lens maker equation. Lens maker equation. The lens maker equation helps us to find probably the focal length or one of the radii of curvatures of a lens, which is supposed to have two surfaces. So the lens maker equations. So let's consider another problem. A converging lens of focal length 10 centimeter, it has a positive focal length, forms an erect image. For an erect image to be formed on a converging lens, it has to be formed at the same position where it has to be formed at the same side where the object is placed. It will not be formed at the other side, just like I explained in the first minutes of the video. Okay, that particular image is 3 times the size of the real object. That means the image height is 3 times the object height, which means that image height over object height, which is supposed to be v over u, will now become 3 h naught upon h naught, which is equal to v over u, which means that v over u is equal to 3. That means v is equals to 3u. And whenever we have an erect image which is formed at the same side as the object, the image is always virtual, because it is always formed by a virtual rays of light. Okay, that is, it is always formed at the inward, in the direction of the inward ray, and it's not supposed to be like that. It's supposed to be formed at the outward ray, that is the other side of the lens. So we say that image distance is virtual. That means v will be negative 3u, and as a result, i'll be able to find I'll be able to make use of the formula, which is plus 1 over u. The question says find the distance between the image and the object. To know the distance between the image and the object, I'll have to understand the diagram. So let's say I have something of this nature, and of course this is the focal length, this is the center of curvature. So if I place an object, for it to form an erect image, the object should be placed somewhere here, that is between the focal point and the pole, that is the middle of the convex lens. And of course, when the rays of light touches so the lens is supposed to converge the light on the other side. So the rays of light should be converged, since it's a converging lens, should converge it at the focal point, and as a result, so the rays of light is supposed to be converged at the focal point on the other end. So I'll have a virtual ray of light in this direction. Okay, just like I explained in the other time. So I should have the other one pass through the center, so that the ray of light will move in this direction, and they will touch each other at a point where the image will be formed. The point where they touches is where the image is formed. So the image produced will be magnified, very, very big, okay, than the object. So just like you can see here, the image produced is 3 times the size of the real object. So the implication is that because it is formed by a virtual ray, that's why we say that the image distance will be negative. That was what I was explaining then. And for us to now know the image, the distance between the image and the object, we need to know that from this point to this point is the object distance u, and of course from this point to this point is the image distance v. So the distance between the image and the object is supposed to be v minus u. Okay, v minus u. So I just need to find v minus u. If the image were to be formed on the other side of the lens, it will be v plus u. Okay, so I have v already, I just need to know the value of u. So 1 over f is 10, equal to 1 over v is minus 3u plus 1 over u. So by LCM, I'll have minus 3u, and of course this will be 1, and then this should be minus 3. So that's equal to minus 2 over minus 3u. So negative sign can go with the negative sign. So I have 1 over 10, which means that 1 over 10 is equal to 2 over 3u. So if you cross multiply, you should have 3u equal to 20, which means that u is 20 upon 3. And of course, 20 divided by 3 is supposed to be 6.67 in centimeters. Okay, and of course we can find the v now. So to know v is 3u. Okay, so that's 3 into u is 6.67, or 20 over 3. I'll prefer that. That's 20 upon 3. Okay, so 3 can actually cancel out with 3, so that v is equal to 20 centimeter. So we can make use of this. V minus U, that is 20 minus 6.67, which is equal to 13.33 centimeters. So this is the distance between the image and the object. I hope you understand this video. I hope you learned a lot in this video. Like this video, subscribe to this channel, and share with your friends. Bye for now.